Welcome back, physicists. Okay, so for today we have momentum. Awesome. What else have we talked about? Impulse. Now, instead of just giving myself purely the impulse, I'm going to give us the impulse momentum because this is a theorem that we saw. So we know that impulse is F force. It's our average force, but that's nice because we don't deal with forces changing a ton. The average force times some amount of time is exactly equal to, and there's a bunch of different ways that we can write this. Now, how would you guys prefer to write it? Anybody have a huge preference? I'm going to do it a couple different ways, and we'll just have three equivalent statements. The way that I would normally plug this in is not the first one, but I could say it's mvf minus mvi. That's one way that we could write it. And I just want to make sure we can see, hey, look, we have a few equivalent ways. Different situations are going to warrant different pieces. Now, you can plug it into any of them. It will work. You're just going to have to pick out and see where do you need to put where. Okay, is there any obvious algebra that one could possibly do here? So let me rephrase that. There is, because that's a yes or no question, what is the obvious algebra that we could do to make that look a little tiny different? Yeah, I'm going to love it, first of all. Instead of saying take out m, there's a better word? Factor the m out. So we can do it like this, vf minus vi. That works all fine and dandy. And it's weird because I could have done it here. Another way that we can represent this is just final momentum minus the initial momentum. And these three pieces right here are all equivalent. Okay. This is a pretty rare symbol, but the word equivalent shows up a lot. Obviously in physics particularly. Do you guys know the symbol for equivalent? Like, we essentially call it equal. Don't sketch this. I just want to see if you've ever seen this symbol. 1/2 is a ratio. Okay. It is the same thing, equivalent, as 4/8 as a ratio. You guys agree with that? Okay. Normally, what symbol would we put between these? Equal. Now, I'm fine with that as equal, kind of. But, like, there's situations where it doesn't make sense to say that they're equal. If I said 1 out of 2 people prefer this, and I say 4 out of 8 people, the ratio winds up being the same, but which one's more meaningful? A survey of 2 people, a survey of 8 people? 8. Like, that's way more meaningful in a real world applied context, right? So this symbol, if you ever come across it, your book doesn't use it, but a lot of physics places do. This is the symbol for equivalent. It's like an equal with an extra 1. Okay. I won't use it, but I want you guys to know that it does exist. Okay. Cool. So that's where we left off. Now, for everything that we've seen so far in the first half of the section, this is for motion that goes in a line, right? We haven't done any crazy spinning stuff yet. This is all linear. And all that means, and just in case, this is straight line motion. Okay, nothing crazy about it. Now, the first 4, 5, 6 sections of our book, everything was linear all the time. And then we got to this idea of torque and all of that good stuff. And we went from dealing with just linear motion to what sort of motion? I need to oil this chair to make that more feeling. I'm dizzy just with that. What was it? Circular or rotational, right? So here is our natural jumping in spot. And I could have swore I grabbed my notes a second ago. Yeah, I did. Cool. All right. So jumping in, we are continuing on from our stuff the other day. And we're going to have a bit of recall stuff that goes on here. Up through the first half of this section, feel okay with it? Okay. So the second part of this, if we talk about linear momentum, which we just call it rho, the second half of 9.1, we are going to focus on this idea of angular momentum. And it turns out, not what we're going to do with it, but when you talk about angular momentum, this idea mixed with some crazy probability and statistics stuff winds up showing up all over our modern model of physics, specifically our quantum models that are seemingly correct with everything that we ever predict with them. Okay, so we have a few little things to knock out first. Right off the bat, I hate it. I wish it weren't. L. It is a capital L that we use for angular momentum. Now, I hate it for a very particular reason. Anybody remember what capital L represented elsewhere for us? Liters, it definitely represents liters, but we also use it for the length of something when dealing with torque. It's the lever arm length. So, obviously we're limited to letters. What I've done historically, and I don't love it, but often what I do is I'll use this fancy L instead. It is entirely up to you. I will try to remember to use the fancy L. There's other places in math and eventually in physics where this L means something different again some more. Not my choice. Okay, so we're going to use L, and I'm going to write it as my fancy capital L. Now, right off the bat, if we check the stuff that we did the other day, right at the impulse momentum, check your notes for me and tell me what did we use to start thinking about how this was going to work. Like we used some pretty basic idea. Like we wrote impulse momentum and I said, hey, recall this. Okay, so Newton hooks it up, right? We have Newton's second law, which tells us that the force of an object, one way to think about this is it's its mass times its acceleration. And this is linear. Now, it's been a little while, but let's check stuff out. We're going to derive it similar to how we did the other day. Now, this is linear. Okay, when we switch, and I'm going to just do an arrow down, I guess, because I'll just do it here, linear. What if I wanted to write this instead of linear motion with angular stuff? Like, we still use a force, but we call it something a little different. What's the force that causes rotation? We don't just call it F. I'm okay with wrong answers as long as somebody shouts out an answer. It's like force. Maybe lever arms are related to it. If you did FR sine theta, or what did we get? Or L sine theta for lever arm. It's a T word. Close. I like it. Tension's a good T word. Tension is what causes centripetal acceleration. I'm cool with that. There's one more. Maybe a special wrench, because if I'm using a wrench, I'm not going to push straight, right? I'm going to try to get it to turn. What sort of wrench do I use to loosen or tighten so I don't over tighten? Torque. Is that what did you say that already? Yeah. Say it louder. Okay, so check it out. When we think about Newton stuff, we make a little change. We have torque, which remember is this goofy tau symbol instead. How do we find it here? Torque is equal to, now the mass certainly matters, but it's kind of wrapped up in somewhere else. Is it easier to spin a big solid disc or a big hula hoop of the same weight? Big hula hoop is easier. Are you sure? Is it easier? Is it easier to spin? I'll just draw it. Would you rather spin this thing that's solid and weighs 10 pounds, or this thing that is hollow in the middle and 10 pounds? Why? Good question. Around this point in a circle. Gosh. I'm going to give you a moment to look back and try to relate this idea. Go back like a half chapter. I'll give you a moment. Now, I remember the piece of notes that I'm thinking of, there's a whole bunch of them, but we did something where we related force and torque, and then mass and, gosh, there's another bigger piece of it, because it's not just the mass we care about. And I'll also go back with you, because I'm going to try to find it. Hey, I see on 209 is where it's starting to show up. Hey, 214 is my page. This is 8.2. Instead of using mass when we talk about things rotating, we have a bigger idea. 8.2, there's a fancy table that's giving how mass is distributed along stuff, right? That is a table that shows us, instead of just the mass, we're dealing with the what? Inertia. Go back one page and you'll see it. Instead of mass, we're dealing with be more wordy.
Momentum of inertia.
Change word. Are you sure it says momentum?
Moment.
The moment. So when we made this transition, and this is like a month ago, so I totally get it. We think of, instead of just mass, we use the moment, which has to do with the mass. It's mr squared depending on the shape, and then it gets less and less depending on what we're trying to spin. So just looking back at these things, the hoop is the hardest to spin. If all the mass is outside, that's the hardest thing. That is mr squared. There's a lovely table. So let's make sure we do the same thing. This is torque. And this is what causes rotational motion. And what's torque? Like, what's the unit on it? It's not just newtons. So you're on a good thought. I'll tell you, mr squared is the standard for a hula hoop. M, mass, is in what? Kilograms. And then the r, the radius, would be measured in typically what for SI? Meters. So if we did kilogram times meters squared, we get that unit. Kilogram meters squared. That's how torque shows up. Okay. Now, furthermore, and we'll fix this. We'll add something to this here in just a second, because what's this I represent? It's the moment. And in my mind, I mix this up all the time. I don't want to tell you what I mix it up with, because you might start doing it. We have the moment of inertia. Okay, and then instead of acceleration, lowercase a, what is it? How do we write the angular acceleration? It's not just an a anymore. It's Greek and feels kind of like an a. Alpha. Okay, this was our angular acceleration. Okay, so I'm going to add a couple little units because I'm off just a skosh here. Our moment is really our kilogram times meter squared. You don't have to erase anything. We're going to fix it. Angular acceleration. It's how fast the angle changes over time. Okay. How do we measure angles if we don't want to have to deal with degrees? Radians. And what's the real unit of a radian? Good. Yeah, it's nothing. No, there's no answer to that. Awesome. Love it. Okay. This one is always weird. It's per second squared. And you can write the word radian up top if you want to, but you don't have to. And the reason that I didn't make you guys erase here is what happens if we do kilogram meters squared divided by second squared. We just have to do this. Okay? And super ugly, the unit game. Do you guys want to watch a little weird video here as a brain break about something that everybody is annoyed with physics, and I assume you are too? Okay. Help me out here real quick. This unit's kind of ugly, right? Like, it sucks. But let's just think about this. Newton tells us that kilogram meters per second squared, that's mass times acceleration, kilogram meters per second squared is what? What's the way to measure force? Newtons. So in brown, don't write it down, but if we had kilogram meter squared per second squared, do you agree that it could just be this? Is that the same thing? Okay, and what do we just now say kilogram meters per second squared were? That's a Newton. So this alternatively could be in this lovely unit, or it could be in Newton meters, which is the equivalent of foot-pounds if you're thinking about torque in the American system. Okay, unit stuff, we're going yak. We're going to finish this and we're going to see a weird video, just something strange that happens in physics. Okay, so we're doing a lot of review stuff. I hope it feels like review. We're going to keep rolling with it. Okay, this, did you remember all of this, or do you look at it now and be like, oh yeah, we did that? Does it feel kind of familiar to you? Okay, cool. So I'm getting some nods and some blank faces. But let's go a step further like we did yesterday. Angular acceleration. I'm going to rewrite this line, but I'm going to change a couple things. So I know that the torque on an object, and just so it's really clear, we are building up right now to try to find impulse momentum, but we're going to do it angular instead of linear. That's all we're doing right now. So I know it's still the moment. I'm good with that. Here's I. And what's, just by definition, what is acceleration? Like not a number, just in general, how do you find acceleration? So that gives you weight. So that's a almost. VF minus VI is just how much has your velocity changed. You need one more little piece to it. Per time. Okay, so a change in velocity over a change in time is what acceleration is. Just how fast does your speed change. But we have angular acceleration. So I'm going to write this a little bit differently. Instead of writing alpha, I'm just going to write out what it is. We have a change in angular velocity over a change in time. And here we are back at just trying to recall stuff from a month ago. If v is linear velocity, how do we write angular velocity again? It's another Greek letter. Louder. Alpha is acceleration. I like where your head's at, though. We have definitely seen it. We saw it in pre-calc briefly. We saw it in here a bunch. Angular velocity is what I want to know how to write down. Not theta, that's our angle. Delta theta you could think of as being the change in the displacement of it. But we have a letter, and I guarantee you guys have it in your notes, in your book. I don't want to just give it to you. I want you to be able to find it. Ooh, let's do that again. Can you draw it on your margin? Maybe. You guys already have your book open to this stuff, so it's a piece of cake. Here's velocity. It's v, or it's that letter. Remember what that letter is? I'm not, but the alpha and the omega. We use omega, which of course it makes sense. It's a W. I think you were doing phi, I think.
Oh, yeah.
But you could have been doing that as well, or you could have been doing this, which is similar. Cool. All right, so here's this. And again, if you need it, I would encourage you to label it. What is delta omega? Change in, what is omega? Look at your page and read it to me. Angular something. Angular velocity. Good. Okay. So here we are. This is exactly what we did yesterday, but instead of m delta v over delta t, we just have the moment over, or times delta omega over time. Okay. One last little step, because some people love fractions, some people don't. And whether you love them or not, let's just not use them. So how do I make this not a fraction anymore? Torque is equal, what should I multiply by? So torque delta t is equal to I delta omega. Okay. Love it. We are almost at our impulse momentum theorem. Like, honestly, we have it. Right now we have our angular impulse momentum, but we're just going to write this a couple different ways just to make sure we can make sense of it. So how would we express this, delta omega? How would you actually find it? Delta anything. It's always the same. It's just a letter that changed. I totally informed us a moment ago that delta v was vf minus vi. Delta y is y2 minus y1 if we think about algebra. How would we write delta omega using that exact same idea? But it's omega, final, and what should I subtract from this? Yeah, it's the same delta anytime we see it, especially in physics. It's pretty much going to be this. All right. Now, just like we saw a few minutes ago when we looked at, I'm trying to remember what it was that we looked at specifically. When we did it here and we distributed, could we distribute here also? Okay, so I'm going to take one line to do this because we're going to get the same 3 equivalent little pieces. So torque times time is equal to I omega final minus I omega initial, or our moment times our velocity. And all I've done is distribute. And all of a sudden, this looks really, really similar to something that we saw yesterday, the last couple days. We wrote up above that the moment is like our mass and omega is our velocity. But we're just moved to angular stuff. And what did you call it when we did mass times velocity? Just MV? What was it? It was momentum. This is the angular version of this, which means this must be angular momentum. Okay, up above we said, hey, here's a symbol that I'm going to use. What are we going to use to represent angular momentum? You probably wrote it. I can see it on your page. What's the unit or the label, sorry? Yep, I'm going to use fancy L. You can or can't. Check it out. It's just this. LF minus LI. Okay. This idea is the exact same thing that we did linear. We just made the switch. So like we saw a moment ago, these 4, realistically, are these any different? Like they look different, but do they all mean the same thing? So these are all equivalent, just like we saw happen above. And then even more so, I will go ahead and define this just underneath, save a little bit of time. When we switch this to the linear version, this is the same as F delta T equals rho final minus rho initial, and we called that the impulse momentum theorem, right? Okay, this is the same thing. We just switched it. Instead of linear, we're doing it how? Angular. Check it out. This is our angular impulse momentum theorem. Okay, for this, I do not have a huge issue if we have this, as long as everybody's comfortable with what we've done. I would like to take a little brain break because it's Friday, half the class is gone. Uh-oh, do you not want a brain break? Are you sure? Didn't look like you wanted one. All right. Okay, so I'm going to trust your guys' judgment. People watching this, if the video finishes or is too boring or whatever the case is, we might come back and do a little bit more. That's not a threat, just for the record. I'm not giving you homework either way. This might be the end of the video. Stay tuned. Or not. I don't know.